In 1.6 modeling exponential growth and decay, there are 2 YouTube videos right off the bat that I would like you to take a look at before we do any of our actual examples. But our goal today is to model and solve common exponential growth and decay problems, including compound interest, half-life, doubling time, population, etc. So below are typical examples which follow the behavior of exponential growth or decay. So we could have financial growth. So when you invest money, it makes more money on that slowly over time. Vehicle depreciation. So typically you hear as soon as you drive a new vehicle off the lot, boom, price of it drops substantially. Population growth. So the more people you have in a certain region, the faster that they will continue to reproduce. Doubling time for bacteria and half-life for radioactive decay. There's one equation that really sums up all of these situations, and it is the formula y equals a times b to the power of t over p. Now this is located in the bottom left-hand corner of your formula sheet, I believe, and it's something that you want to be aware of. So I'm going to break down all these variables to start with. So a is your initial amount. So however much you are starting with. Y is your final amount, whatever you are finishing with. B is your rate of change. So if something's doubling, the rate of change is 2. If it's cut in half, then the rate of change is a half. If it is a percentage, so for percentages, it is 1 plus or minus the decimal value, and we're going to do some of those here today as well. T represents the time, and P represents the period. Now what the period is how long it takes for B to happen. So if it says population increases by 4% every 7 years, then my B value would be 1 plus 4%, and the period would be 7 because it takes, sorry, I missed a 0. Oops. It takes 7 years for it to grow by 4%. So we're going to try some examples, and hopefully it'll become clear to you. So example number 1, assuming that in 1990 the population of Canada reached 30 million, if growth trends remain constant, it is predicted that the population will double in 40 years. So that should tell you 2 things. First part says model the situation in terms of a doubling equation. So remember, I'm just going to write this on the side. It wants it as a doubling equation. Okay, so the final amount, I don't really know, because it will depend on the end date. How much am I starting with? Well, I'm starting with a population of 30 million. Now, instead of writing 30 million, I would just write 30, and remember that we're talking in millions of people. So my initial amount is 30 million. My rate of change, well, this is doubling. How long does it take for it to double? 40 years. Therefore, my period is 40, and my time will be t, because, well, it depends. Do I want to know the population in 40 years, or 50 years, or 60? I can plug in different values for t. So B then says, what will the population of Canada be in 40 years? Now, using logic, if it's 30, and then it takes 40 years to double, in 40 years it should be 60 million. Now, this is a good opportunity for me to test if my formula actually works. So I want to know the final amount after 40 years, so I'm going to plug in a 40 there, and I get y is equal to 30 times 2 to the power of 1, or my final amount is equal to 30 times 2, or 60 million. So this means that my formula does in fact work. Okay, I can use logic to confirm it. C then says, how long will it take for the population of Canada to reach 40 million? So I want my final amount to be 40 million. And how long means I'm going to find T. Okay, so I'm going to use my same equation that I had in A. So 30 times T to the power of T over 40. My final amount is 40, so I'm going to plug that in. So 40 is equal to 30 times 2 to the power of T over 40. This one we're going to solve algebraically. If there's an exponent on one side, how am I going to solve it? Well, I need to write it logarithmically once I get rid of that coefficient. Now I can simplify 40 over 30 to 4/3. So 4/3 is equal to 2 to the power of T over 40. Now logarithmically, I have log base 2 of 4/3 will equal my exponent. And my last step is to times the 40 over. So the amount of time it will take for the population to reach 40 million will be 40 times log base 2 of 4/3. Now I don't know that value off the top of my head, so I'm going to go to my graphing calculator, and I'm going to evaluate it. So I have 40 times the log of 4/3 divided by the log of 2. And I get an answer of 16.6. So how long will it take for the population to reach 40 million? 16.6 years. And that's our first example of exponential growth. So it's growing because if it's doubling or increasing 2 times in 40 years. Example number 2, to check for thyroid deficiency, radioactive iodine with a half-life of 8.2 days is injected into a person's bloodstream. A healthy thyroid absorbs the entire radioactivity from the iodine. Model this situation as an exponential equation that determines the percent of radioactive iodine in the bloodstream after any number of days. So here I have days, this is good. Okay? So if I just start, I'm not going to worry about this percent yet. I'm just going to think about what I'm given. I'll go in a different order. Start with the Y. What am I given? I'm given a half-life. Our half-life is our rate of change. And how long does it take me for it to be cut in half? Well, it should be 8.2 days. Okay, so I can pull up that from the equation right away. When it says model the situation as an exponential equation that determines the percent, well, what does percent start at? It should start at 100 and then decrease over time. Okay? So I'm going to represent my equation as y is equal to 100, because I'm starting with 100%, times my rate of change, which is half, to the power of t over the period it gives me of 8.2. In B, it says, how many days should it take for only 10% of the iodine to remain in the bloodstream? So this 10% tells me my final amount. So I want my final amount to be 10. I'm starting at 100% with a rate of change of 1/2, and it takes 8.2 days to be cut in half. Now we're going to solve this in a different way. Okay, so I'm solving for my exponent of t, but I'm actually going to graph it to solve. So graphing is an acceptable strategy for sure, and it's fairly quick once we know what we're doing. So I go in there, and when I go into my y equals, I'm going to set my y1 is equal to my left side, which is 10. For my y2, I'm going to do the other side of the equation. So 100 times a half, I'm going to put it as a decimal, 0.5, to the power of x divided by 8.2. Now before I press graph, I'm going to go to my window and I'm just going to change it. I know there's going to be something at y equals 10, so I'm going to change it to 20 just so I can see even more. And then I'm going to press graph. I don't see anything. Well, I know it's going to be going down over time, and I know that I'm starting at 100%. So if I'm starting at 100%, maybe I should change this to 100. Okay, so I can kind of see that it's going down, but I need to see more x's. Might know where they intersect, I might not. I'm going to change that to, I don't know, 39. And now I can see where they intersect. To find the intersection point, I do my second trace, intersect, enter, 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 and I get a corresponding x value of 27.2, we'll say. So how many days should it take for only 10% of the iodine to remain in the bloodstream? Well, 27.2 27.2 days would be our estimated amount. I was just checking to make sure I rounded that right. There we go. So we can solve it graphically by doing y1, y2, or we can solve it algebraically like the last one. In our third example, it's going to give us something completely different. It says the following data represents the cooling of a cup of hot chocolate over time. Use exponential regression to find an equation in the form T is equal to A times B to the power of T, where T is the time in minutes and capital T is the temperature in degrees Celsius. Determine the temperature of the hot chocolate after 35 minutes. Well, it gives us a table of values. If it gives us a table of values, we can enter that table of values into our calculator and let it do a lot of the work for us. So to enter a table, I press Stat, Edit. Now, in my first list, I'm going to put the first column, so 0, 5, 10, 15, 20. And in my second list, my second column, so 60, 54, 48, 44, and 41. Okay. So I have all that entered. And now all of this information, I want to make a calculation on it. So I'm going to press Stat, Calc, and it says I want an exponential regression. So I'm going to scroll down to 0, which is exponential regression. I'm going to press Enter on it, and Enter again, and it will give me that equation. Okay? So I'm going to copy that equation, and I'm going to be really detailed on it. So A is equal to 59.366, and B is equal to 0.9809. Just going to check those, make sure that's right, good. Okay. Now what does the A represent here? Well, that represents my initial temperature. Now, we know the initial temperature was exactly 60, but if you notice, none of these have decimal values, so they are approximations. So, yeah, the approximate initial temperature would be 59.366. Okay, kind of makes sense. Now, B is going to represent our cooling rate. Now, remember, when it's a percentage, it's going to be 1 plus or minus. In this case, it's going to be minus because it's cooling. So 1 minus what will give you 0.9809. Okay, well, if I subtract it from both sides, I'm going to grab the calculator here. I get a decimal value of 0.0191, or about 2% per minute. So that's just extra information for you. So the hot chocolate's cooling by about 2% per minute. So it says here, though, determine the temperature of the hot chocolate after 35 minutes. Okay, well, I don't know the final temperature. I know this was my original. I know my rate of change is this per 1 minute, and the time is going to be 35. So from here, I can literally just plug this into my calculator. And it's going to tell me that the temperature after 35 minutes is going to be about 30.2 degrees Celsius. Now, it's probably challenging to remember what all those steps were, so I'm going to write them down. To enter our table, we pressed Stat. Edit. Under List 1 is the first column. List 2 is the second column. And then we press to do our calculation second. Oh, sorry. We press Stat, Calc. For me it was 0, but it should be exponential regression for X reg. So if it gives you a table, utilize it. So continuing on, we are on example number 4. It says the population of BC in 1998 was 1.5 million. The average rate of growth, per year, determined this time, during this time was 1.8% annually. What should the population be in 2010? Okay, so try this one on your own. Let's see how we do. So I don't know the final amount. I'm starting with 5.1 million people. It's increasing by 1.8%, so it's increasing. So my rate of change is 1.018 to the power of T over P. Now my period's going to be 1 because it says annually. Now it wants the population in 2010, so 2010 subtract 1998, so 12 years later. Okay. So I want my time actually to be 12. From here, I can just plug this into my calculator. So I have 5.1 times 1.018 to the power of 12, and I get 6.32 million. So hopefully that one went well for you. And we're going to continue on then to example number 5. Example number 5, put a star beside this because it's a special formula that you're going to probably have to look back on in order to remember how it works. So in this one it says an investment of $500 earns interest at 6% per annum. So that line means per, and the A means annum, which means year. So an investment of $500 earns interest at 6% per annum, or per year, compounded semi-annually. So that means twice a year. Write an exponential equation that calculates the amount, A, of the investment after T years. Okay. I don't know my final amount, but it wants me to use the letter A. So the amount is equal to my initial amount, which is 500, times my rate of growth, or rate of increase, which is going to be 1 plus, now my 6%, I'm going to turn that into a decimal, and then I have to divide it by the number of compounding periods per year. So this compounds twice a year. Okay. Now, it is going to be to the power of the time, which it wants us to use the variable t, over the period. Now, how long does it take for it to earn interest? Well, it gets compounded twice a year, so halfway through the year, it'll get compounded. So my period is going to be a half. Lots of people want to put 2 there, but if it was 2, then that would mean it's earning interest every second year. Okay. Now I can clean up this formula because it's pretty messy, and I can clean it up to A is equal to 500 times 1.03 to the power of, okay, so t divided by 1/2, dividing by 1/2 is like multiplying by 2, so to the power of 2t. Then says, how many years to the nearest year will it take the investment to double? Well, if it doubles and started at 500, then it's going to go all the way to 1,000. So 1,000 is equal to 500 times 1.03 to the power of 2t. To solve for t, let's go algebraically on this one. Divide by my coefficient. So I have 2 is equal to 1.03 to the power of 2t. Now I can write it logarithmically. So log base 1.03 of 2 will equal 2t, and then I will divide both sides by 2. So the amount of time it should take is, just going to picture that out, 11.7 years. Okay, now just to read this question again, it says how many years to the nearest year will it take the investment to double in value? Well, it's going to double partway through the 11th year, so I'm going to round it up to 12 years. And that is the end of exponential growth and decay.